All right, Sydney, this one's not just for you. This one's for Garmin and for Olivia and for you and for the rest of you out there in the rest of the world that might choose to watch this. If you choose to watch this, hey, please subscribe to my channel.
They want to learn chemistry.
All right. So, when I look at this, the KSP, as soon as I see KSP, I know I'm dealing with an insoluble solid, which doesn't make sense. We're dealing with the solubility of an insoluble solid, but we want to know how insoluble is it? How limited is the solubility? So as soon as I see that the copper salt iodate, I want to write an equation, CuIO3 2 solid, and what is that going to dissociate into for that little bit that does?
Cu.
And how do you know, Anya, that it's 2 plus?
Because of the charge, or the subscript on the bottom by IO3.
Pretty much is going to be the charge here plus iodate. Now iodate's not on our chart over here. Which one is on our chart?
C.
Chlorate. But chlorine, bromine, iodine are all in the same family. So if chlorate is ClO3 minus, bromate is BrO3 minus, iodate is IO3 minus. Okay? So they're all going to do the same thing, same family, bond the same way. So I know that that's -1. Anything that has a halogen in it, polyatomic ion, they're all going to be -1. Anything with the sulfur, selenium, tellurium in them is going to be -2. Anything with the phosphorus or arsenic is going to be -3. So I know it's copper +2, and then plus what else?
IO3 squared. Okay, IO3 minus squared.
Not squared. That's going to be my KSP expression, but in just the equation for the dissolution of this in water, it's going to be that. So sometimes they ask just write the equation for the dissolution of the, and that's what you would write. Okay? You must include the charges. I just gave a test to my pre-AP kids. Total net ionic equations. Over and over again. What's the definition of an ion? The charged particle. 90% of them didn't put the charges on the total net ionic equation.
Is that why there were so many students in your AO?
Yes. More should have come. So when I'm looking at this now, so I know it says the KSP is given as 1.4 times 10 to the -7. It's going to equal, this is where it's going to be the Cu2 plus times the IO3 minus squared. So they may want you just to write the equilibrium expression for the dissolution of the copper 2 iodate. All right? But now, if I want to figure this out, I know that in my ice baby, I have 0 and 0, but I'm going to get plus what?
It's plus X on.
Plus X.
And plus 2X.
2X. So then I'm just going to plug into here. So I'm going to say X times 2X squared is going to equal my 1.4 times 10 to the -7. So it's going to equal 4x cubed. So divide by 4, take the cube root. X is equal to my Cu2 plus. But what's the concept? What's the question actually asked for?
Calculated solubility is 1.3.
Its solubility, the copper iodate. We want to know that, but for every one of these, we got one of those, so X is equal to that as well. But you need to make sure you identify that. Okay? And what does that equal? I'd say it's about 3.3 times 10 to the -3rd.
Yep.
Did I do my mental math right?
Oh yeah.
So we can't just write x equals 3.3. We have to write.
No, you need to define what X is, because answer the question. Answer the question. And the question's asking for the solubility. Its is that.
Does it have to be at the end, or could that be like our?
It doesn't matter, I mean, anywhere, just as long as you know what X is. You define what X is. Okay? Any questions on that? That's just straight up KSP.
What if it was plus 2x? Like, how would you like do the ratio from C to CiO3 to?
I mean, if this was a 2 as well or something,
Yeah.
well then it'd just be half.
Okay.
This would be 1/2 of that, and you just show that. I would write this is equal to 1/2 of this, and then multiply it, it's equals whatever.
What?
It's just like in math. You just identify what x equals. That's all you're doing. Just what is x? Answer the question. He was just saying if there was a 2 right there. That means this would be 1/2 of the value. And by the way, it's 3.3. So if this were a 2 and x came out to equal that, and this was a 2, then this one would be a 1. It's got to be half of that. But that's rarely ever. I've never seen it before like that. Okay, so that's the first type, one of the main types, just straight up KSP. The next one's what type of problem?
Common ion.
Common ion problem. So, if we calculate the solubility of CaF2, but this time now it's in this molar. So now when I do my KSP again, Steve, Ca, I'm always going to write my expression. It's going to dissociate it to Ca2 plus 2F minus. Okay? So now my initial, this is 0, but what's my F minus initially?
0.025.
0.025. It's actually 0.025, but it was a letter. But I'm on a mission from God, trying to change myself and the world. Giving the 0 the respect it deserves. Everybody calls it an O.
Poor guy.
All right, so now what's my change going to be?
Minus x and plus x and plus 2x.
Plus x and plus 2x. Okay? So my KSP is given as 4.0 times 10 to the minus 11 is going to equal to Ca2 plus times my F minus squared, which is going to equal. Oh, I know, lucky bounce. Better be lucky than good sometimes. It's going to equal x times 0.025 plus 2x squared. But what can we assume?
The 2x is negligible.
The 2x is negligible. Okay? So assume 2x is negligible. Good word to spell. Assume 2x is negligible, therefore 4.0 times 10 to the minus 11th divided by 0.025 squared is equal to x, which is my Ca2 plus concentration, which is my CaF2 concentration. And if I do that mental math in my head, I think it comes out to 6.4 times 10 to the minus something.
Yes,
Hold on, what?
Why, if the NAF is like 1F, is that real? So that doesn't affect the CaF2?
No, well, it's affecting the F minus concentration, which affects this whole equilibrium. Because I'm adding it in, we're putting it all in together. The solubility product says this times this cannot exceed that.
But then why is there F2 and CaF2 and F only?
Okay, all right, what's this gonna break up into?
And then
How many F's?
1.
Just one. So if I put in 0.025 of this, what's this gonna be?
1.
Well, 0.025. This is 0.025. We don't care about this. So I'm starting with that much in the solution from the NAF, and then I'm adding in more from the CaF2. So what does this actually come out to?
6.4 times 10 to the negative 8.
All right, now, yes ma'am.
So let's say that like NA
So let's just say it was, MgF2.
Yeah, MgF2. How would that affect what you're doing in the problem?
That would make my initial concentration 0.05.
Okay.
Because it would go to, I didn't finish this, I need a. Okay, so you're gonna get 2 Fs for every 1 you put in, so you just have to double it. I think we did one practice problem like that the other day. Go back and look at your notes on that one.
You just double it.
You would just double it. Again, it's the same thing as we did way back in molarity, where I asked what the concentration of the ions were in the multiple choice question. Okay, I gave you the molarity of the substance, and then you had to figure out what the concentration of the ions were. It's the same thing. Okay? Nothing new under the sun. Now, what if, instead of saying it was 0.025 molar, what if we said to which, 0.15 grams of NaF was added to 100 milliliters of the, of solution.
On the molarity.
You just have to do another step and find the molarity of that using the molar mass, and then do it the exact same way. Okay? So if you're giving grams of common ion, the volume will be given, change it to molarity, and then do it the exact same way. Got that?
Got it.
You might need to make sure you know how to do that. Don't look at me like that.
No. I got it.
Okay, I'm trying to give an innuendo here, so,
Seems like a fair question to ask.
okay? All right. Now, we've done a lot of KSP. Remember, which will precipitate first is going to be a bonus, so I'm not going to go over any more of those. Okay? How do we determine will a precipitate form?
Like Q.
That's where we solve for Q, right? The first thing we have to do is do a dilution, so we need to be able to do that type of problem. I've done a bunch. Do we need to do any more of those?
It would help. Maybe.
One more.
I think there's, let's see if there's one in, I think there's one here.
Exercise?
Yes,
Oh,
it's
yeah,
perfect,
exercise.
it's perfect. Next page.
Yes.
I remember, that's what I remember how, this is the one I wanted you to do. Okay, so let's just do this one. Okay? And your key word is will this precipitate, or what will we observe? Will we observe a precipitate or not? Okay? That's always going to be mean Q problem. The other thing is that you have the KSP and you have the molar solubility, you have everything. So you know it's going to be a Q problem. Take time to ask questions if you're a little stumped.
So when you mean negligible, like, it means like a number like 0.0, like over mole given added to the exponent, right?
In other words, to 2 or 3 sig figs, it's not gonna change the value of that number. It's so small.
Okay.
Get 5.37.
Why don't you ask me? I got 1.63.
Alright.
Yeah.
For what?
Hey, it's all 1.6. Huh? That made me sick. What'd you get?
What's my issue for CE curriculum,
Why
right?
don't you cube it?
What?
And then point 0.02 for IO.
I just got straight six.
Well, I don't mind science and
Don't cube it.
No, why are you cubing?
Should we cube it?
Yes.
No. Wait, you do?
Are we cubing it?
No.
I don't
When
think
you, when you
I'll say
multiply
yes.
the concentrations together.
Bob's doing it.
Do we have to cube it?
I don't know, I read it.
Wait. Cause then.
Alex seems yes, and I like Alex answer.
Well, it's a bit, I see the 3 with the nitrate, but this is gonna be here, you're gonna need to cube that one.
Oh, times 22.0.
I didn't say you were wrong.
Well, because I know that, will this precipitate, so I'm gonna always write that expression. That's the thing I'm interested in.
What is it, please?
So it's gonna go to CE, and what's the charge gonna be, what's the charge gonna be on CE?
3 plus.
3 plus, everybody has that, right?
No.
Who's, no? What's the charge on iodate? We just talked about on the last problem. Matthew, what's the charge on iodate? We talked about it on the last problem. It's a halogen, so what do I know the charge is?
1.
-1. Since there's 3 of them, what must be the charge on cerium?
3.
+3. Okay, plus, generally speaking, whatever that number is gonna be the charge up there. So it's gonna go to cerium 3 plus 3 IO 3 minuses. Aqueous, aqueous. So my KSP expression is gonna be cerium 3 plus times IO 3 minus cubed.
Oh my god.
Why was that an issue?
I mean, it shouldn't be an issue.
I just made it an issue.
Yeah, I made an issue too. Not your fault.
All right, now, the thing is we have to find out what these are. We have to find the value of Q to see, does it exceed this given value of KSP? So this is where we have to find my cerium concentration.
27.
Cerium is going to be, I'm putting in, my cerium's coming from right here.
750.
So I'm gonna go 750 milliliters, but I'm adding it to 300 milliliters. So what's my total volume gonna be? 1,050, so it's gonna be 750 divided by 1,050th of the original concentration, which is 4 times 10 to the minus third. And what does that number come out to?
2.8 times 10 to the negative 3. 2.9 times 10 to the negative.
We can go 3 6,
Two point
baby.
86.
Okay, now what's my iodate gonna be?
300 divided by 1050 multiplied by 0.02. Yes.
Times the, yeah, it's probably easier to write 0.0200. And that turns out to equal
5.71 times 10 to the negative
times 10 to the negative
3.
3. And that's my IO3 minus concentration. So what must I do with those two numbers?
And add it,
Multiply them all.
I gotta put it, and I gotta put them into my QSP expression, which is gonna equal 2.86 times 10 to the minus third times 5.71 times 10 to the minus third cubed. Right?
Yes.
Okay. So, what does that come out to?
5.41 times 10 to the
So 5.41 compared to 1.9 times 10 to the minus 10, which one's bigger?
5.41 times 10 to
So Q is bigger, right? So what does that mean?
the
So you're gonna say Q is greater than KSP, therefore a precipitate will form.
So let's say that we, for some reason, forgot to keep, like I said, the same number. And then you got the wrong answer, but you still said it will form. How would they, like, would they give you the right answer? Or would
Probably
they-
get, maybe, if it's 2 points, you might get 1 out of 2.
Okay.
So you can just guess.
You could have.
You gotta have something, you can't just guess, you gotta have something back up your guess.
I can
You don't get,
It's an educated guess.
what are you getting, Josh?
I got 5.32 times 10 to the negative 10.
That's what I got.
Yeah, I got that too.
I think it's just significance.
Okay.
Did you just use 2 sig figs? Yeah. Okay. Regardless, it's bigger, right?
Yes.
Okay, yes, sir.
Would a precipitate form if Q is equal to K?
If Q, we asked that question yesterday. If Q is exactly equal to K, no precipitate is gonna be formed because these two numbers are exactly equaling this. Now you will have an exact saturated solution. Okay, most saturated solutions are gonna have some solid sitting on the bottom. Okay, that's how you're gonna know it's saturated, solid sitting on the bottom. That's why a lot of the problems always say there's always some solid sitting on the bottom. But in this case, you'd have, if the Q came out to equal K, you would have a saturated solution with no solid sitting on the bottom. But if you added any more, it would just go to the bottom. Okay? So we good with KSP?
Yes. This problem's nice.
All right. So, now let's look at straight up equilibrium. If we go back to our original note set,
I got brown. I got black, I got I used to do that.
where was it?
Hey, Rob, I don't need
What's it? Okay, so I am on the very last page of the first set of notes.
The Chatelier is crucified. What a, I just like that name. The Chatelier.
So good.
Dr. P. Making it up.
So, yeah. All right, I'm on the very last page of the first set of notes.
Make a tier list of all the service you like.
So, predict the shift in the equilibrium position that will occur for each of the following processes when the volume of the, and we probably need to imply there, the volume of the container is reduced. In other words, like a piston pushing down. Okay? Do we remember the rule? Okay, when you decrease the volume of a system at equilibrium, the equilibrium is going to shift in the direction,
Of the least amount of gas or aqueous gas.
not, you're close.
So whatever it's like, whatever loses it, we
Just
should.
gas.
Just gas.
So aqueous isn't.
No, because that's gonna be a liquid, it's gonna be down at the bottom, and the container size isn't gonna matter.
I wrote down in my
That's
notes.
for something different.
That's for something different. Okay, we only include aqueous and gas in the equilibrium expression.
Okay.
But pressure is only going to, the change in concentration is gonna be like or changing the volume is gonna be changing the pressure of the gas.
Okay.
All right, and again, the way I think about this is that, well, if it's going, closing in on it, those gases are all going to be getting closer and closer. They want to make room for themselves, so some are going to go back down into the liquid. Okay, or fewer moles of gas that are going to recombine. So, given this right here, which way is the equilibrium going to shift?
The right direction.
Why, Josh?
Because it has less
Moles of
moles of
gas. You're going from 6 moles of gas to 0 moles. We don't look at solids and liquids, we just ignore it. We're only interested in gas for the Chatelier's principle. What happened to the value of K?
It stays the same.
Stays the same. What's the only thing that affects the value of K?
Temperature.
Temperature. Good. The preparation of gaseous phosphorus pentachloride, so this one right here, you decrease the volume, which way is it going to want to go? To the right, because you're going from 2 to 1. But then the reaction of phosphorus trichloride with ammonia, okay? You get that crazy thing.
It stays the same.
Well, how many moles of gas do we have on the right?
It's 4 and 4.
How many do we have on the left?
4.
So basically, it's not going to shift. Okay?
What if volumes increase?
If volumes increase, the exact reverse.
Okay.
It's going to favor the side with more moles of gas. But for here, which of the following reactions predict how the value of K changes? So now, here we're going to change, the temperature is going to be increased. So now we are going to change the value of K. So how will K change? Looking at this.
K increases.
Well, you've got 2 different things going on, A and B. What do we know about delta H on this one?
It's
Endo, how do I know it's endothermic?
It's a positive.
It's positive. So where would heat go in my equilibrium? On the left, so heat's over here. So if I increase the temperature, I'm increasing over here, right? So it's got to always go away from what you're heating. It's always going to go in the endothermic direction. So if we're increasing product, what's going to happen to the value of K?
The K value increases.
Products will react.
K is equal to products
Minus
over reactants. Right? That's, you're thinking thermochemistry, it's products minus reactants and the delta H. Okay? Since it's a ratio of product to reactant, if it shifts right, we're getting more products, which means K is going to get bigger. But in this one, Delta H is negative, so where does heat go?
It heats on the right side.
Heat's over here. So by increasing the temperature, which way is the reaction gonna go?
To the left.
To the left. And so what's gonna happen to K?
Decrease.
It's actually gonna decrease. It's gonna become more reactant favored.
So it's directly proportional to temperature.
Always in the endothermic direction. Okay? Yeah, I mean, it depends on whether or not, I mean, here it's increasing, here it's decreasing. It all depends upon which way you're going.
Yeah.
Okay, so you can't really say it's directly proportional to the heat, because it depends whether it's positive or negative. Endo or exo. All right, now. Let's look at some other examples of Le Chatelier's principle. What happens if I add an inert gas?
No effect.
Nothing, right?
Wait, inert gas to B?
Inert gas to any equilibrium. Okay, we did these in the past, but let's just review them. I am on page 666 in the textbook.
Always like.
Thomas!
Oh, it's the devil's hand.
Okay,
Where, what page?
This is also one.
666. Oh, 666.
Yeah.
I remember the 666, alright, go.
What?
No, I'm joking.
What?
There's no 666.
all right. So, we're looking at this, okay? Now, how will each of the following changes? So if I have, you're adding O2. I add O2 to this. Which way is the equilibrium going to shift? Okay, always away from what you're adding. So if I add this, again, do the old teeter-totter. So I'm gonna miss. I got the teeter-totter. We're at balance. Then we put some oxygen in on this side. Now it's out of equilibrium. So that's not what the question is asking. What does the reaction have to do to regain equilibrium? It has to move to the right to use up that oxygen. In terms of kinetics, you increase the concentration of O2. What does that mean about the rate of the forward reaction? It increases because one of the 4 ways to increase the rate of the reaction is to increase the concentration. So the forward rate is going to increase, but the reverse rate's not. So initially it's going to be going to the right, until this starts building up, and then that speeds back up, until finally they meet back in the middle where the 2 forward and reverse rates equal one another. B, the reaction mixture is heated. So what do we need to know in this case?
Delta H.
Where delta H is, right? Where's delta H go in the equation?
On the right.
How do I know? Delta H is less than 0. Okay, that means it's negative, which means it's exothermic, which means that heat goes over here. So if I increase, the reaction mixture is heated, which way is the reaction going to go? What direction would be? Left. Left. Okay, now, what would happen to the value of K then?
It's gonna decrease.
It's going to decrease. Right? Now that's not part of the question, but it could be.
What if reaction mixture is cooled?
If it's cooled, that means it's like you're taking heat off the teeter-totter. So now it's got to go that way to replace the heat. Okay?
So would heat be like a product in this?
In this case, yes. And again, that's like paper burning. The fire is like a product of the reaction.
So you go
Yes, sir.
towards-
Hold on. Yes, sir.
So, based on the reaction is indirect and thermic, that's how.
You know whether the heat goes on the right or the left. Okay? Exo, it's on the right. Endo, it's on the left. Endo, you're adding heat to make it happen. Exo, the heat's being produced as part of the reaction. C, the volume of the reaction vessel is doubled. We just did that one. So we double the volume. Which way is it gonna go? Made the volume bigger. More, it's because it's gonna create more moles of gas. Okay? A catalyst is added. No effect. Will a catalyst affect the value of K? No, doesn't affect it. It just gets you to equilibrium faster. The total pressure of the system is increased by adding a noble gas. No. Are any of these values going to change? No. Temperature didn't change, the volume of the container didn't change.
Wait, so for C, you said it shifts to the right? I mean, if SO.
I didn't say it. We said it's going to shift left.
It shifts to the left.
Why?
Because there's more moles of gas.
Yeah, well, it's double, it's gonna move, and then it's.
Okay, the reaction always shifts to the side. When you increase the volume of the container, it shifts to the side with more moles of gas because you got more space to fill up. So you need to have more moles of gas to fill up that space. And then SO3 is removed. So SO3 is over here, but SO3 jumps off the teeter-totter. So it's got to shift right to replace the SO3. And again, that is a way in which you can cause a reaction. This is one of your questions on your lab, is you can be removing the SO3 as it's being made, and that forces the reaction to keep going to the right. That's what they do in industry. If a reaction is going to tend to go towards equilibrium and they're trying to collect this product, well, then they're going to have to figure out a way to extract it to keep the reaction moving towards the right. All right, are we good with Le Chatelier's principle?
Perfect.
That should be easy money. It's gonna be on there. So what's the only thing that affects the value of K?
Temperature.
Temperature. So if K, for this one, Kc is equal to 10 for that reaction, I made up a number. What's Kc gonna equal now?
Five.
Kc of that equation is 10.
So five.
I hope.
No, yeah, it should be 10.
Shouldn't be.
Square root of 10.
Wait.
Wait, is
You're
K
pretty smart, yeah.
No, it doesn't change because it only changed by 10.
But we have a completely different equation. Okay, is that equation going the same direction?
No.
When you reverse the equation, what do you do to the K? Reciprocal. Products become reactants, reactants become products. It's 1 over. What do you do with coefficients? Become exponents. Okay, the coefficients are exponents. So K is going to be 1 over 10 to the 1/2.
Man, didn't see that one coming.
Okay, remember, in equilibrium, the coefficients are your exponents. So if you multiply an equation by 2, or in this case by 1/2, then you have to raise the K to that power of 1/2. When you flip an equation, write it the other way, since it's a reversible reaction, you can write it either way. Products become reactants, reactants become products, therefore you're going to get the reciprocal of the value of K.
Sounds important.
He's recording it.
Forgot about that one for a second.
Now it's.
He's probably gonna post it.
I'm just kidding.
That's happened before.
I'd be like, oh, who are you?
All right, so now if I take H2CO3 going to H plus HCO3 minus, Ka1 is equal to Ka1 is equal to 1.76 times 10 to the minus 5. But then I go HCO3 minus goes to H plus CO3 2 minus. I get Ka2 is equal to 5.6 times 10 to the minus 11. Okay? So if I have then H2CO3 going to 2H plus CO3 2 minus, Ka3 is going to equal,
It's like a system of equations.
very much so.
That it,
You multiply.
Do I add, subtract, multiply, divide?
He's gotta be right.
Square, square root. I'm adding the equations.
Multiply.
You got 4 options.
It's probably multiply, division.
You multiply.
What?
When you add equations, you multiply K's.
I'm really glad you decided to do this.
You add equations, you multiply. So the 3 things about K, 4 things about K. If you reverse an equation, you take the reciprocal. Because products become reactants, reactants become products, you just flip the ratio. If you multiply an equation, you raise K to whatever you multiply it by. K to that power. If you add equations, K's multiply. The 4th thing, the only thing that's going to change the value of K in a given equilibrium is temperature.
Can you go over the story of someone not recording?
No.
No?
Not right now, no.
I'm not trying to distract anybody. Just want to know more information.
You like story, you want story time.
Born is fun. You haven't watched the documentary.
Now, what's this document?
HBO Max.
Okay, so this is everything we just said. And there's the exact example. Okay, so I'm going to not do equilibrium review. Okay? So, again, if we just reverse the equation, we're going to take the reciprocal. We multiply, we raise K to that power, we add the equations, we multiply the K's.
Can you post this in Google Docs for me?
Yes.
What?
Okay? Now notice down here that if K is greater than 1, obviously products are greater than reactants. It's product favored. K is less than 1, reactants are bigger than products. It's reactant favored. The bigger K is, the more product favored. The smaller K is, the more reactant favored it is. So again, when you look at that chart of just the K's of acids, okay, you look at this chart back here. At the top left, K's are very large, which means we have 100% ionization. Everything's going to the right. Very, very product favored because your K is very large. On the top, on this acid chart over here at the very top, HClO4 goes to H plus ClO4. It says the K is very large. It's a very strong acid, 100% ionization. Those are 6 strong acids. But as you go down, the acids are getting weaker and weaker, meaning less and less are ionizing. So the K is getting smaller. So by the time you get over here to water, H2O, breaking up into H plus and OH minus, the K is 1 times 10 to the minus 14th. That means that very few water molecules actually break apart. Most of them are going to stay together as H2Os. NH3, well, look at OH minus breaking apart into H plus and O2 minus. It's less than 10 to the minus 36th. In other words, it pretty much doesn't happen. Okay? So K tells us whether or not the reaction is product favored or reactant favored. Bigger K, product favored. Smaller K, reactant favored. It's a math thing. It's a ratio of products over reactants. All right. So these now are our different types of equilibrium problems. We can calculate, what's the difference between Kp and Kc?
Kp is pressure while Kc is concentration.
Okay, same exact expression, products over reactants, coefficients raised to powers. It's just, are you expressing it in terms of pressure, atmospheres, or in terms of concentration, molarity? All right? Keq is just a general K, an equilibrium constant. It can be either Kc or Kp. We're going to find when it's an acid or a base equilibrium, we're going to change it to Ka or Kb. For solubility product, we just call it Ksp. All right, so the subscript just kind of describing the type of equilibrium. All right, so this is here. All information is given. These are different three different types of where we have to calculate Kp. Where all information is given. Just plug it in. Don't expect one like that. Okay? So you're just given the equilibrium, the reaction, you're given the equilibrium concentrations of all of them, but then you just plug it in. That's too easy. That would be an insult to your intelligence for me to give you a problem like that. And I refuse.
I'm okay with mine.
I refuse to insult you. I have more respect for you than that.
I don't have any
Okay?
respect.
I have much more respect for you than that.
Yeah. I have for a while.
I don't know who I am.
Because I know the hose. My bag passes to the brim.
Okay, so the second type is the initial amount of a reactant is given and the percent reacted. And we did one in our problem set that it said like 29% reacted. Where is my problem set? Where's my big problem set? I don't have that sitting here somewhere. These are all 2013 ones. Do you have your original problem set?
2001?
No, the 8-page one.
Oh, 8. This one?
Yeah. I have one somewhere, just not sure where. So, if you look at your example on 1988 right here, it's an example of that type of problem. Okay? We already went through and did this. We've done that, I think pretty much did the whole problem, I believe. Okay? So notice here, just to go through it, an 89.7 gram sample of antimony pentachloride is placed in an evacuated 15-liter container at 182. Immediately, again, when I'm reading that, it's a gas, I have a pressure, I have a volume, I have a temperature, I have an amount. My brain just goes piv nerd. Well, I want to calculate the molarity, which is moles per liter. Grams divided by molar mass divided by volume. And then remember what? When we did pressure, remember that PV is equal to nRT, but pressure is going to equal N over V RT. What is N over V? So it's going to equal molarity RT. So to save yourself some time, you calculate the molarity here. You can just plug that in and just multiply by RT and get the pressure. Okay? So now, but this is where it says SbCl5 goes to SbCl3 plus Cl2. So then it says, okay, well initially, how much, well we calculated the molarity. What did we calculate the molarity to be, the initial molarity?
0.020.
0.020 molar. Someone agreeing with me on that one? That's my initial concentration.
Yeah.
That's what you get when you do number one. Okay? My initial, we haven't put it, it hadn't reacted yet, so my initial is 0 and 0. So now I'm going to have a change and an equilibrium. Well, I don't know. The question is, calculate Kp or Kc. So I don't know Kp. So in order to calculate Kp, which Kp is going to equal SbCl, well, okay, I'm going to do Kc, sorry. SbCl3 times Cl2 divided by SbCl5. Now again, problem solving, y'all. If this is the question, I have to know all three of these. I cannot have two variables. You have to know them all. So I know initial, but these are equilibrium. I have to know my equilibrium concentrations to put them into the equilibrium expression. So I need to know my change. Well, what does it tell me? 29.2% decomposed. So my change is going to be 29.2? 292 times 0.2, which is going to be 0.584, 0.0584?
Yeah, that's what it
Just 0.0584 or 2 zeros?
0.00.
That's how much decomposed. Well, if this is how much decomposed, how much of this got made?
Passive amount.
The same exact amount, right? So then I'm going to know my equilibrium concentrations, and I plug it in, and I get my value of Kc. Right? So the percent decomposed, that's telling me my change. In essence, when we're going the other way, it's telling me my X. Should have worn I have a shirt that says find X and then it points to it. There it is. But got a tennis match today, so I had to go SP.
Who do you apply?
Donahue out of Anniston. No,
Donahue.
that's what I thought. Yeah, it's a private school out of Anniston. Okay. And we didn't like C. Don't worry about the C on that one.
Obviously.
All right. So here's another good one. 1983. Okay? Now, let me just say, one other variable of this, and I don't know if I'm going to find a problem or not. Instead of saying 29.2% decomposed, it could say that at equilibrium there was 0.0050 molar Cl2. Well, if I started at 0, what must have been my change?
0.005.
So it's got to be plus that, minus that amount. And remember, if this was a 2, it's going to be minus 2 times that amount. Right? So there's 3 types of just calculating Kp or Kc. Number 1, you're given all 3, which you're not going to have. Number 2, a percent is given. Or number 3, you give an initial amount and one of your equilibrium amounts. So basically they're telling you what the change is going to be. You just got to go through and set up your ice table. Does that make sense? So you have those 3 types of finding Kp problems.
Yeah, if it was to 4 molars,
It would be 2 times this, which I would think would be 0.01.
oh, I was looking at the other example.
No, yeah, it would be, no, if this is how much, it would be minus 0.010 if it was a 2. So then it'd be 0.02 minus that. Okay? I'm just making up numbers on it, so just to kind of show you. All right? And we did a bunch of examples, so go back and look at those examples. All right. Remember this type of problem. First off, what would be the pressure in the atmosphere if nothing happened? PV equals nRT. Okay, so we get an initial pressure. Okay, so P is going to equal, we got to do that, I got to get a number for us. Oh, we already got it, 0.08 atmospheres. This right here came from PV equals nRT. This came from part A. Okay, PV equals nRT. You have this many grams, divide by the molar mass to get moles. Okay, and we know R, the temperature is 375, divided by the volume 1 liter. So we get the pressure, came out to 0.8 atmospheres. Now, here's the deal. SO2CO2. So there's my initial. Again, the question, it says calculate the partial pressures and then give the expression and solve, calculate the value. So I need to calculate the equilibrium. So that means I have to find all three of these pressures at equilibrium. Well, I know it's going to be minus X, and plus X, right? But I can't have two variables. What else do they tell me? They give me the what? What's this? Total pressure at equilibrium. What's making up all of that pressure at equilibrium? What's combining together to make that 1.43 atmospheres of pressure?
The pressure of the SO2.
All three of them, right?
The
So we know now that 1.43 is going to equal 0.8 minus X plus X plus X. One of the X's cancel, so you just subtract. So 0.63 is equal to X, which is equal to the pressure of the SO2, which is equal to the pressure of the Cl2. Well then, at equilibrium, this is going to be minus 0.63. So this is going to be 0.17 atmospheres. This one's going to be 0.63. And this one's going to be 0.63. Then, you just plug into your KP expression. Y'all, when it says total pressure, use Dalton's law. That's your key phrase, total pressure. So when you're taking this test, you see the term, assuming it's on there. You see the term total pressure, you underline it. What's adding up to that total pressure? Okay? Now again, if this was a 2, what would this be?
2X.
Plus 2X. Plus 2X. You can still do the problem. Okay? It all adds up. Okay? When you see the term total pressure, that's another way of helping us. It's just a roundabout way of giving us the change. You just got to calculate it using Dalton's law. Okay? Confidence rising. I got this. All right. Let me give this back to you before I forget.
Sorry, no more opening day.
All right, so those are 2 types of equilibrium. That's our first type, or right there. And so our second type is calculate the equilibrium concentrations of all reactants given an initial concentration and the Kc or Kp. That's where you let X equal, and then here's what I put in red. Remember the problem-solving method when total pressure is given, okay? Then, what does it say? Examples 1983 and 1992 on that packet for that. Q problems. They're all over the AP test. These are the type of Q problems. Given all equilibrium concentrations and the value of the Kc, the question asks, what direction will the reaction go to reach equilibrium? Or is the system at equilibrium? If not, what direction will it have to go to reach equilibrium? So you solve for Q. If Q is greater than K, that means that you have too much product. Product over reactants, right? You have too much product, so which way does it have to go? Left. If Q is less than K, now you have too many reactants, so it's got to go right. Q equals K, you're at equilibrium. I'm going to post all this. The other question it will ask, and there's some practice problems. I hope it's the same. This is pretty old. It might have been from a different book. They'll be close to that in your textbook. Okay? So given concentration of two solutions, this is what we just did. Is Q greater than KSP? These are the ones we did at the beginning of class. Will a precipitate form? That's your other Q problem. So the first Q problem is the system at equilibrium? If not, which way will it go? Which way is it going to move to reach equilibrium? And then the second one is, will a precipitate form? You guys are fading on me. Don't fade on me.
We didn't have one break today.
Oh. Neither did I.
3:40.
Yeah, why don't you give yourself a little break?
Hey, let's start at 3:40, guys.
Because you have a test tomorrow. I'm trying to get you as ready as possible so you can do well.
I think you work too hard.
It's because I care.
Well, yeah, you gotta care about yourself a little.
Yeah, that's true.
That's what God made weekends for. And tennis. That I get to play, not necessarily always coach. But. All right, then we talked about Le Chatelier's principle. Okay, these are all the factors we just talked about with Le Chatelier's principle. And then changing the temperature. Notice how it's all kind of big, bolded, cap. Changing the temperature is the only thing that changes Kp or Kc. And then our KSP problems. Now, down here in red, remember this is what we talked about yesterday. Changing the volume does not change the molar solubility. Okay? So if I have a beaker with a solution. I'll just keep it simple. It's silver chloride. And I have some solids sitting on the bottom. And I have Ag plus and I have Cl minus floating around in there. And right now I'm going to have 1 liter of solution. And I begin to evaporate water off. I begin to heat, well, the water just evaporates. I don't heat it up because that changes the value of K. But the water just evaporates. I leave it open for a week. And then the water level is now at 0.5 liters. What's going to happen?
The concentration will stay the same.
Okay? Some of this, obviously, there's going to be not as much room, not as much water. So some of this is going to begin to precipitate together and form more solid. Okay, because once the water evaporates, now my concentration, KSP, which is equal to 1.8 times 10 to the minus 10th, is equal to Ag plus times Cl, Cl minus. That looks like a K. All right? So when the water evaporates, these are going up. Because all of a sudden now these ions are in less water. So the reaction is going to have to shift left in order to make, they can't exceed this number. So they're going to keep shifting left, keep shifting left. Water evaporates, keep shifting left until this times this gets back to equaling that, which is going to be the same concentration as it was at 1 mole, at 1 liter. Now, there'll be fewer Ag plus and Cl minus ions actually in solution, but the concentration will be the same. Now, I come back in, ooh, a bunch has evaporated off. I need more solution. So I go in and add more water, and I bring the volume up to 2 liters. Now what's gonna happen?
More Ag plus and Cl minus.
More and more now, this is gonna start dissolving to fill up all this extra liquid until when?
Reaches equilibrium.
It gets back to the same equilibrium concentration it was before. Because the KSP is the molar solubility, it's a ratio, it doesn't change with volume. Y'all getting that? You sure?
Yep.
Did you get that? Okay. All right. 12 minutes. What do you want me to go over?
So if it's like 500, like in an equation, if you, if we have to, ever have to do 500, like, so if it's given as like 500K, we don't have to add the 270.
Right, because it's already in Kelvin, but it always has to be Kelvin.
Can we just do another problem for the general equilibrium socket?
Can we do another common ion problem?
A common ion? Sure. Is there one in that packet that we hadn't done yet?
Figure it out.
Yeah, you'll figure it out. You'll be fine.
Sorry, guys.
I wrote it all down.
I don't have to do it.
What about the one with the Spanish?
This isn't common ion, but when is equilibrium reached?
But it zeroes out a constant.
On the graph, how do I know when equilibrium is reached?
It's a flat line.
When it flat lines, when it goes flat, when the concentration remains constant, then the forward rate and reverse rate are now equal. Okay? So in this case, it's gonna be time, whatever unit that is.
For 2 seconds they said
I saw it. They can pause it.
It's 1988.
1988?
We already did that
No,
before.
the second to last page.
Oh, we did 1988. No.
Look, 1988.
Oh, the two 1988?
That's a Le Chavalier's problem, 1998.
Okay, just a comment.
Okay. 91.
All right, here we go. Whoops, forget that.
There's another 1988.
I think you get a vote.
Okay, $5.
Alright. What are you gonna say? She's gonna go?
I thought it was $5 originally.
No, it was fine. And I did make you pay, because I wouldn't have paid you for it. I probably made it.
Oh, bring it up.
Yeah. Pizza party, pizza party. That'd be expensive. Why? 14?
Change the recipe or something.
Why?
How many credit cards do you have? Two. You don't have credit card? No.
Yeah.
Debit card? You use debit card? Cash. Cash is better, right? You get pennies.
Okay, now, you probably will not have time to work this one out,
Picture.
okay? So, let's just do it together. Okay? So if I have silver chromate, the first thing I have to know is the KSP, and that's gonna be given. Somebody look up the KSP of Ag2CrO4 for me.
Nine times 10 to the negative 12.
Okay, so that's given. 9 times 10 to the minus 12. So I know that in pure water, I'm gonna go Ag2CrO4 solid is gonna equal, it's gonna go to 2Ag plus CrO4 2 minus. Right? So my KSP, 9.0 times 10 to the minus 12 is gonna equal what and what?
Ag squared.
So it's gonna equal X, well, if I just wanna write the expression, Ag plus squared times the CrO4 2 minus, which is gonna equal 2X squared times X, which is 4X cubed. So X is gonna equal, somebody get that for me?
.31 times 10 to the minus 4.
Okay, so now I know that it's 1.31 times 10 to the minus 4th molar. That's my solubility of my silver chromate. So what's gonna happen to that solubility if I add some silver nitrate?
It's gonna decrease.
Decrease always. Because if this goes up from a secondary source, I just start dumping some silver in, this times this can never exceed that. So what has to happen to my chromate?
It's decreased.
It's got to decrease. So it's got, as this goes up, it's gonna shift the equilibrium to the left. It's gonna cause this to decrease, this to come out of solution. Okay? So, because I'm giving in grams, what do I have to do?
Calculate the molarity.
Calculate the molarity. It's gonna equal 1.7 grams divided by the molarity, molar mass of 170 grams per mole, divided by 0.1 liters, is gonna equal, that's gonna be 0.01 divided by 0.1, 10 to the minus 2 divided, so it's gonna be 0.1.
Yeah, exactly.
Okay?
That's right.
Someday you'll be able to do it without
Yeah, I know. That's pretty impressive.
that. Now notice I picked the number nice and
Yeah.
even anyway. So, now in my, going through this, my initial concentration now is not 0 of silver. Here, hey, this is a good one too because, well, not really.
It's all right.
0.1 is 0 and 0, but this is gonna be plus 2x, and this is gonna be plus x, right? So now, 9.0 times 10 to the minus 12 is gonna equal 0.1 plus 2x squared times x. But again, what can we assume?
2x.
Because this is so tiny that 2x is gonna be very, very small compared to that. Okay? So, 0.1 is going to be 0.01 or 10 to the minus 2, so that's gonna come out to 9.0 times 10 to the minus 10 is equal to x, is equal to my silver chromate, concentration. So notice what happened to the solubility. It went from 10 to the minus 4th molar, 10 to the minus 10th molar. Okay? So the only thing different between just normal molar solubility and common ion is you just don't start at 0. Whatever the common ion is, you just have that value. Okay? All right. Pack up. We're getting out of here because I got to get to a tennis match.